Welcome to The Explainer. So today, we're diving into something that is literally hiding in plain sight. We're going to track the evolution of a single everyday word, fraction. It's a term we all start using as kids, but what you might not realize is that the mathematical definition of a fraction actually evolves and fundamentally changes as we age and progress through school. Let's unpack exactly how our math language grows up right alongside us.
Okay, let's dive right into this, because I want to start by challenging a massive assumption almost all of us brought with us from elementary school. When you hear the word fraction, what immediately pops into your head? For most of us, it's a visual, a pie chart, a partially eaten chocolate bar, or, let's be real, it's a slice of pizza. But is a fraction really just a piece of a shape?
You might actually be surprised to learn that modern math standards completely bypass that whole fuzzy pizza slice myth right from the get-go. Instead of parts of a shape, early standards define fractions as exact, precise locations on a number line. So it's not a shape at all. It's a specific coordinate, an exact point in numerical space.
To really wrap our heads around this, let's map out the journey. We'll kick things off at year 3 with the grade 3 basics, then we'll move into the year 5 shift, and finally, we'll hit year 9 for that high school precision.
Section 1. Early years, unit blocks.
So in 3rd grade, the main goal is to treat fractions not as abstract, weird concepts, but as tangible building blocks. And the absolute foundation of this is something called the unit fraction, which we write as 1 over b. The strict rule here is that it's the quantity formed by one part when a whole is partitioned into b equal parts. From there, the standard builds the general fraction, or a over b. That's simply the quantity formed by a parts of size 1 over b. Essentially, a general fraction is just a collection of repeating unit blocks. You're literally just counting them. And this brilliantly illustrates exactly why the number line completely beats the pizza slice. Just look at 5 over 4. Under the old pizza definition, this is an impossible thing to explain to a kid. I mean, how do you have 5 slices of a pizza that only has 4 slices? You literally can't. But on a number line, 5 over 4 makes perfect sense. It's simply defined as exactly 5 hops of size 1/4. You just keep hopping right past the number 1. It's precise, it's logical, and it's infinitely expandable.
Moving on to Section 2, Grade 5, the division shift.
Now, as kids grow up, their math has to grow up with them, right? By grade 5, the entire interpretation of a fraction officially shifts. Students are now taught to interpret a fraction as the division of the numerator by the denominator. So, a over b actually means a divided by b. Why is this such a big deal? Because it formally shifts fractions from a visual layout into a mathematical operation, a quotient. But there's a huge catch here. At this stage of development, a and b are strictly expected to be whole numbers, integers only.
Which brings us to Section 3, the fuzzy language crisis.
Once students leave middle school, the word fraction kind of turns into this loose, ambiguous, visual shorthand. Honestly, it becomes a lot like the word average, a word we use casually all the time, but one that lacks strict mathematical rigor. To see this crisis in action, just consider the mathematical expression, the square root of 2 over 5. Visually, it looks exactly like a fraction. It's got a number on top, a line in the middle, and a number on the bottom.
So the crucial point here is this actually a fraction? Well, visually, sure. But mathematically, based on the elementary rules we literally just learned, the answer is absolutely no. Remember the rule? The top and bottom must be integers. The square root of 2 is an irrational number. It's a non-repeating infinite decimal that just goes on as 1.414213 forever. Because that top number isn't a whole number, this is not a true elementary fraction.
Let's fix that in Section 4, High School Math Precision.
High school math swoops in to solve this exact vocabulary confusion by giving us incredibly precise terms that tell us exactly what kind of numbers we're dealing with. The first major upgrade is the rational number. Fun fact, rational actually comes from the word ratio. The formal definition here is any number that can be written as a over b, where a and b are integers and b doesn't equal 0. This applies strictly to integer relationships. So 3 over 4 is rational, -5 over 2 is rational, even the whole number 7 is rational because you can just cleanly write it as 7 over 1.
The second classification is the irrational expression. If the numerator or the denominator cannot be written as a whole number, boom, the expression is irrational. This is exactly where our square root of 2 over 5 belongs, right alongside expressions like pi over 3. Understanding this distinction is massive. You can't simply find a common denominator for the square root of 2 over 5 and 3 over 5 by just multiplying by integers. They belong to completely different number families. Their mathematical properties are fundamentally different, even if their visual layout looks exactly the same.
From there, the vocabulary just explodes to cover everything. We use the word quotient as the universal catch-all term for any expression of a divided by b, no matter what they are. If we throw in variables like x, y, or z, we call them algebraic fractions. And if we get super specific, where both the top and the bottom are polynomials, we upgrade the language once again to a rational function. The vocabulary becomes highly specialized to perfectly match the complexity of the math.
All right, time for Section 5, Concept Check. Name that expression.
Now, what's really interesting about this is how we can completely ditch that fuzzy word fraction and test our new vocabulary. Take a look at these three distinct mathematical expressions. Visually, they all share that exact same top over bottom layout. But how would you formally classify them now? A is negative 7 over 12. B is the square root of 3 over 2. And C is x plus 2 over x squared minus 4. Think about the rules we just covered.
Okay, let's see how you did. Step 1. A is absolutely a rational number because negative 7 and 12 are both strict integers. Step 2, B is an irrational expression because the square root of 3 is an infinite, non-repeating decimal, not an integer. And step 3, C is a rational function because both the top and bottom are polynomials containing variables. Look at that. We've completely bypassed the word fraction and identified exactly what we're working with.
Finally, Section 6, Why Math Literacy Matters.
So why even bother upgrading our language from grade 3 all the way up to grade 9? Well, it all comes down to math literacy. By recognizing that the word fraction is often just describing a visual layout rather than a strict number classification, you totally empower yourself as a learner. We just saw how the math standards build understanding logically, starting with counting unit hops on a number line, shifting into division, and finally demanding the precise terminology of rationals and quotients in higher math. Upgrading your language stops calculation confusion before it even has a chance to begin, because you know the exact rules for the specific number family you're looking at. Which leaves us with a truly fascinating question to walk away with. Today, we watched a simple childhood word evolve into a complex system of logical classifications. But if our basic math words are designed to fundamentally change and upgrade as we grow, what other foundational concepts, whether in math, science, or language, are sitting in your mental model right now, just waiting to be upgraded? Thank you so much for exploring this with me, and definitely keep questioning what you think you already know.